Okay, so these are your conservation of momentum notes. The objective is that you would be able to use this equation to solve for unknowns in a collision. So the equation that we have is down at the bottom of this screen right here. You can see it. It is just basically that the momentum of one of the objects initially plus the momentum of the other object initially is going to equal to the final momentum of each object added together. So after they have collided. So this is specifically talking about when two objects are colliding and they can be moving or not moving. It doesn't really matter. But you can see in the first picture before the collision, ball A has momentum and ball B has no momentum. That's because it's not moving. After the collision, though, ball B gains momentum. So if we had the masses and the velocities, which remember that's what momentum is, it's mass times velocity, we could find what the final momentums would be there. So if you look at this equation down here, we have that the mass of ball A times the velocity of ball A, that's initially. If we add that to the mass of ball B plus the velocity of ball B initially, which this is going to be 0 because the velocity of ball B is 0 at the beginning, that should be equal to the mass of A times the velocity of A final, so whatever the final velocity is, and plus the mass of B times the velocity of B final. Now, notice that the masses are not going to change during the collision. So mass A and mass B, they're going to be both the same at the beginning and at the end. What's going to be changing are the velocities. Okay, so if we think about this, if we have a couple of skaters, okay, we have a reckless ice skater is colliding with another skater who's standing on the ice. Is it possible for both skaters to be at rest after the collision? Well, so let's draw a picture. So we have our reckless ice skater moving across the ice, and here's the other ice skater just standing here. If we'll say this is ice skater A, okay, the reckless one, and then ice skater B. If ice skater A was moving, that means that it had momentum. Okay, so if we say that the momentum of A, let's just pick a random number and say that it was 10, and that is kilogram meters per second. It hits B, which has no momentum because it is just standing still. At the end, after the collision, can they both be at rest? The answer to that is no, they can't be at rest because of the conservation of momentum. So if we add up these two at the beginning, so at the beginning, the total momentum was 10, well, at the end, afterwards, it also has to be 10. So at the end, they could not both be at rest because of the conservation of momentum. When the initial momentum is 0, so what if both objects have a momentum of 0, so they're just standing still? Momentum is going to be conserved as well because as they are pushing, so we're thinking of an example of where objects are pushing each other apart. So here we have two girls. They're just standing there at the beginning. So this is the initial momentum would be 0. At the end, they're moving. Well, how can that be? Well, we would define one of them as having a negative velocity. So we'd say like this is the negative and to the right is the positive. And they're going to be direct opposites of one another. So if this is -5, this has to be +5. If we add them together, get the total momentum afterwards is still going to be 0, which is what it was at the very beginning. Okay, so here's an example problem. We have a 63-kilogram astronaut on a spacewalk when the tether line to the shuttle breaks. The astronaut is able to throw a 10-kilogram oxygen tank in a direction away from the shuttle with a speed of 12 meters per second, propelling the astronaut back to the shuttle. Assuming that the astronaut starts from rest, find the final speed of the astronaut after throwing the tank. Okay, so our two objects are the astronaut and then the tank, the oxygen tank. So our equation is the momentum, or mass, times velocity, and this will be of the astronaut, plus the mass times velocity of the oxygen tank. That's at the beginning. It's going to be equal to the mass times velocity of the astronaut at the end, plus the mass times velocity of the oxygen tank at the end. So the mass of the astronaut at the beginning is 63. The velocity of the astronaut at the beginning is 0 because it's starting from rest. The mass of the oxygen tank is 10. The velocity of the oxygen tank was 0 because it was again starting at rest. So overall we actually just have a 0 initial momentum. My mass didn't change, so we have 63 for the astronaut at the end. The velocity of the astronaut, that is what we are looking for. We're finding the final speed of the astronaut, so we're looking for that. The mass of the oxygen tank, again, didn't change at all. So we have 10, and then the velocity of the oxygen tank is 12 meters per second. It's moving away from the shuttle, so I'm just going to say that's a negative 12 meters per second. That'll help figure out what the actual velocity of the astronaut is, whether it would be a positive or negative number. So I have 63 times my velocity of the astronaut, which is what I'm finding, minus 120. So if I move that over, I have 120 equals 63 velocity of the astronaut. And then I divide those two out, and we get 1.9, and that would be meters per second. It came out to be a positive number, which just means it was going the opposite direction of the oxygen tank, so it was moving back towards the shuttle.